In this episode of Chapter 17, we'll be talking about precipitation. So in the previous video, we talked about molar solubility, how much of something will dissolve if you put it in water, for example. In this installment, we're going to talk about whether or not we're going to form any solid, depending on how much of each of the ions are present in a solution. So a sort of relevant to the human body, so I know a lot of students are interested in biology and biochemistry and things involving the human body and even animal bodies, if you're interested in veterinary school, is the formation of gout or kidney stones. And gout and kidney stones are crystals of what's called calcium oxalate. So calcium and the oxalate ion is the C2O4. It has a KSP of 2.7 times 10 to the minus 9 at 25 degrees Celsius. Okay, so the question is, could I be forming kidney stones in my body right now? Okay. So let's take a look at some concentrations. So let's say right now I have the following concentrations in my body. My calcium concentration is 9 milligrams of calcium per 100 liters of blood. Okay, so 9 milligrams of calcium 2 plus per 100 milliliters of blood. Right, and in order to do our problems, the KSP is related to molarity, so we need to convert that to molarity. So we have 1 mole calcium 2 plus is 40 grams. So my molar concentration of calcium is 2.2 times 10 to the minus 3. And let's say that my oxalate concentration is 25 micrograms per 100 milliliters. 250 micrograms per 100 milliliters. Oops, that should be a times, not a plus, equal. 1 gram is 10 to the 6 micrograms. And oxalate is roughly 90 grams per mole. So my oxalate concentration is 2.8 times 10 to the minus 5 molar. Okay, so given these concentrations, will a precipitate form? Okay, will I make calcium oxalate crystals? So we always want to make sure that we have handy our dissolution equation. So solid calcium oxalate dissolving into calcium ions. And I'm just going to say oxalate ions. Well, let's use the actual formula. C2O4 minus. Okay, so given this information, the easiest way to determine simple yes or no, will a precipitate form? Find Q. Okay, because remember, Q tells us which direction an equilibrium will go in order to establish equilibrium. Okay, so finding Q will simply give us the yes or no answer. Right, so if I have my Q expression is the same as my K expression, just like before. So we could say QSP And we're going to find out that Q equals 6.2 times 10 to the minus 8. Now remember, KSP was 2.7 times 10 to the minus 9. Right, so in this case, Q is greater than K, so my reaction goes left. And if my reaction goes left, I'm forming solid. Okay, so the answer is yes, stones will form. Okay, so if the question is simply yes or no, will precipitate happen, calculate Q, okay, given the concentrations that are present. Now the question is, how much solid will form? Right, and then in that case, we need an ice table. Okay, because anytime you have to calculate equilibrium concentrations, that's what we have to do. So we want our equation. Right, and our initial concentrations for calcium and oxalate. And 2.8 times 10 to the minus 5. Right, so since Q told us the reaction is going left, we are going to have a minus X and a minus X. Let me notate that. Q says go left. All right, so my reaction is going to be forming solid. So I'm going to be losing some ions and forming solid. Right, so that's my change line. Let's come back to blue. My equilibrium line will be 2.2 times 10 to the minus 3 minus X, and 2.8 times 10 to the minus 5 minus X. Right, now let's take a look. Our K, let's come back up here. Our K is 10 to the minus 9. And our initial concentration of calcium, 10 to the minus 3. So we can say for the calcium, X is small. All right, 10 to the minus 8, or 2.8 times 10 to the minus 5, that's close enough, right? We need to keep one of the X's. So if I'm going to figure out which one, my larger concentration, I can assume that X is small. All right, so let's solve for X. So KSP is going to be 0.022 times 2.8 times 10 to the minus 5 minus X equals 2.7 times 10 to the minus 9. Right, we run through that calculation and we find that X equals 2.7 times 10 to the minus 5. Right, so our equilibrium concentrations .022 minus 2.7 times 10 to the minus 5 is still 0.22 molar. And that is our equilibrium concentration of calcium. And we have 2.8 times 10 to the minus 5 minus 2.7 times 10 to the minus 5 means that almost all of that oxalate has been used up. Right, that's our oxalate concentration. So what we're showing here with these equilibrium concentrations, this is left over. After precipitate forms. Okay, so that tells us, because the calcium concentration and the calcium oxalate concentration are 1-to-1. So for every 1 liter of blood, (2.7 times 10 to the minus 5 moles of calcium oxalate are present. Okay? And that's the solid, right? Remember? Right? Now let's back up, take a look at what we have. All right, because I want to make sure that this is very clear. So if X, so if I normally dash these out in the solid column, but if I didn't, I would say 0 for the starting concentration, plus X and plus X. Right, so this is how I know how much solid will form, because X is the amount of solid, okay, in molarity. Right, so that's how I can take X equals 2.7 times 10 to the minus 5 molar and make this statement. Okay? So let's convert that to sort of a practical number, right? So great, we've got that many moles of calcium oxalate formed. So in the human body, there's about 5 liters of blood. In a normal adult body. Right, somewhere between 4.5 and 5.5 liters of blood. So if I've got 2.5 times 10 to the minus 5 moles of calcium oxalate per liter times 5 liters times 128 grams per mole means that there are 0.017 grams of calcium oxalate. So about 17 milligrams of crystals in my body. Right? Kind of fascinating, because gout and kidney stones cause all kinds of health problems. Right? So if I have a significant mass of crystals in my body, those form in between my joints. They form in various parts of my endocrine system. Bad news, right? So here's a question. Would drinking more calcium affect things? Oops. You don't want to do that. Right? So drinking more milk, for example. Right? Let's use Le Chatelier to answer that question. Let's take a look at our equation. Right? Here's our dissolution equation. So if I increase the amount of calcium in my body, that shifts the equilibrium left and makes more solid. Right? So common ion effect, Le Chatelier, all go hand in hand. So if I have some kidney stones and I start increasing my calcium intake for whatever reason, the effect is that we get more precipitate. Or in this case, more crystals. Okay, so this is how common ion effect and solubility actually take place in the human body, right? There's a real life example. Now let's talk about our next topic for this video, which is percent completion, or how much has precipitated. Or we can say percent completion. Okay, so if the normal amount of oxalate in the blood is 2.8 times 10 to the minus 5 molar, and that means through our calculation we figured out that the remaining calcium was 0.0022, and the remaining oxalate was 1.0 times 10 to the minus 6. Right, so what we want to do is take what's remaining and divide it by the original concentration. Or again, percent remaining. I think percent remaining is often an easier way to think about it, because we actually take what's left over. And let's think about it in terms of, this is our equilibrium concentration. Right, so percent remaining times 10 to the minus 6 divided by what we started with, times 100, means that we have 3.6% remaining. Remember, this is the initial concentration, and this is the equilibrium concentration. Equilibrium concentration divided by initial concentration times 100. Right? That means that 96.4% precipitated. Right? And the rule of thumb for percent completion is that we say precipitation is done, precip is quote-unquote done, when percent remaining is less than 0.1%. Okay, so that's going to do it for this video. When we come back, we're going to talk about selective precipitation, and that probably is going to finish out our chapter for us. Okay.